Welcome to another episode of I-24 Motion. My name is Yanbing Wang, and I help the team develop a data post-processing pipeline in order to improve the quality of the data coming from the computer vision algorithm. Today, I will show you this post-processing component, where the input is a raw detection and tracking data from upstream video processing algorithms, and the output is the trajectory data that is recently released on our website. In today's video, I will show you the known issues in the raw tracking data and why a post-processing step is necessary. I'll walk you through briefly the two algorithms that I developed for solving the data inaccuracies from tracking, specifically the algorithm for fragment matching and the convex formulation for trajectory smoothing. Lastly, I'll show you the results and the ideas for future improvements. Note that the algorithm mentioned in this video are detailed in the paper on arXiv. You're welcome to check it out. I'll only be going over some high levels in this video. Previously, we showed you this time-space diagram, which records every single trajectory passing through this stretch of Interstate 24 during the morning rush hours. You can already see some macroscopic traffic phenomena, such as traffic waves. It opens up the door for many new research ideas on traffic science. However, when we zoom in closely, you can see that there are still some inaccuracies. For example, we see horizontal gaps of various width. These are caused by various reasons, such as the geometry of the testbed. When vehicles are passing underneath bridges, the detections are occluded for about 50 to 100 feet. There are also other upstream hardware and software artifacts that cause these gaps. In some cases, we have a collection of cameras being offline, which causes part of this highway not being covered. The cameras are moving over time, so the homography transformation we computed earlier slightly drifts over time, and we have computational boundaries, meaning not all the detection and tracking are processed on a single machine. The computation is actually distributed amongst multiple servers, which causes the information between servers to be discontinued. All of these issues result in tracking interruption, and we see short and choppy fragments instead of continuous trajectories. So the first problem we want to address is fragmentation by grouping fragments that belong to the same objects together to form more complete trajectories. The second type of problem is some miscellaneous detection errors and noisy signals, which I will show you a convex program to fix them downstream. Okay, so let me first show you an algorithm for fragment matching, which is called the online negative cycle canceling. This is based on the classic graph algorithm to solve the minimum cost flow problem. And here I've extended this algorithm into an online version to better adapt to our specific problem. I'm going to show you a simple example of how it works. Here I have 4 fragments in this tiny time-space diagram, and we can by eyeball categorize them into 2 sets, each indicating a trajectory or an object because the fragments within a set appear to lie on the same path in the space and time domain. The goal of the fragment matching is to determine if any fragments should be combined into a complete trajectory, so this is a typical assignment problem. One problem formulation for solving this type of problem is by formulating it into a directed cyclic graph and solve for the minimum cost circulation. This is a standard formulation, and I'm going to be briefing through it quickly, but basically, we can represent the fragments as nodes and connect those nodes with directed weighted edges. And the direction has some sequential meaning, and the weights represent the matching likelihood or the probabilistic meaning. For example, the probability that a trajectory starts or ends with a certain fragment, and the likelihood of combining 2 fragments together, and so on. And to know which fragments should be combined together, we will run this algorithm called a negative cycle canceling. This is a well-established algorithm based on iterative improvement. So we construct the graph and keep finding a cycle on the graph where the sum of the edge costs on the cycle is negative. And we're going to reverse the edge direction and costs on that cycle. So this is part of the procedure for updating the residual graph. And we keep repeating this procedure until there's no more negative cycles can be found. At this point, we have reached the optimality, and we can retrieve the final matching solution by tracing the reversed edges in the graph. In this example, fragment 1 and 3 should be matched, and fragment 2 and 4 should be matched. Again, this is a well-known problem formulation and algorithm. You're welcome to check the reference if you'd like to learn more. I want to talk a little bit more about the online extension of this algorithm. The reason we need to extend it online is that the negative cycle canceling is a batch algorithm, meaning that all the data has to be present all at once to construct this graph. In reality, the I-24 motion system produces millions of fragments during a typical recording session of 4 hours, and this could result in a huge graph about 4 to 5 millions of nodes and edges. Finding a negative cycle on this huge graph is a very expensive operation. This motivates us to find an online extension which we can deal with the streaming data coming in order of time. So the basic idea of this online algorithm is that we can formulate the data association as a rolling horizon type of approach. It means that we can keep a cache with a small amount of memory that only keeps all the data from a short time window and move this cache forward in time. When we see new fragments, we update the graph by adding new nodes and edges, doing negative cycle canceling operation, and remove the nodes and edges that represent older data. In this way, we can effectively keep the graph size small and run much faster. How this works is that we're building upon the previously best matching solution from all the available data that we have seen so far. So for example, we've already had a matching solution for the first 4 fragments. And now the 5th one is a new one, and we need to decide where to place it. Based on the relative position of the new fragment with respect to the previous ones, there are many possible scenarios. So for example, the new fragment could represent a new object that we've never seen before, or a continuation of an existing trajectory, or it could be a false positive, or it could alter an earlier assignment. Luckily, the graph algorithm can help us decide which scenario it is based on the matching cost we assigned for connecting the new fragments to any of the existing fragments. Here's an example. Let's say that the new fragment 5 alters an existing matching solution, which is 1 and 3 are combined and 2 and 4 are combined. The graph on the left is the residual graph representing the temporary matching solution up until fragment number 4. Now the new fragment comes and we represent it with new nodes and edges. In this case, let's say that the edge connecting 1 and 5 has a lower cost than the edge that's connecting 1 and 3. And that is to say that before we see fragment 5, we match fragment 1 and 3 because they have a good matching probability. But now we've seen 5, it has a higher matching probability with 1, and it conflicts with 3 because there are time overlaps. So fragment 3 is unfortunately singled out. So the key operation here is to find the minimum cost negative cycle, which is shown in orange. This cycle symbolizes the logic that I just explained. We want to redo the matching between 1 and 3, but connect 1 and 5 instead. Now we can say that the updated graph on the right is optimal, meaning that there's no more negative cost cycle. We can actually prove that this is true, but for simplicity, I'll skip the proof in this video. If you're interested in the details, please refer to the paper, which I will include in the description box below. So what's important is that this online version allows us to free up some memory space. We don't need to hold all of the data in our memory all at once, but instead it keeps a small cache where the optimal matching solution can be retrieved at any time. There's only one step necessary for each iteration, which is to find the mean cost negative cycle. And this keeps the runtime relatively linear with respect to the number of fragments. Okay, so that's the fragment matching or the fragment association step. The next step I want to quickly introduce is a convex program for rectifying trajectory data. So more specifically, after fragments are matched, we will have some missing data in between those matched fragments, so we want to impute them. There are other miscellaneous errors such as the detection errors and noisy signals, and we want to smooth out the data. This is important because we want to use the data to analyze, for example, driving behavior, and the higher order derivative quantities such as the speed and acceleration should be within a reasonable range. If we don't smooth out those data, and then if we take numerical differentiation, the signal will get extremely noisy. So the way I solve this problem is by explicitly encoding those errors in the measurement model. So in this case, a trajectory measurement will have missing data, some noises and outliers that represent those detection errors. So then this boils down to a regularization problem. We can formulate this optimization problem to minimize a combination of residual error, smoothness of the higher order derivatives, as well as identifying those outliers and removing them. And this formulation is not perfect because it regularizes every single trajectory independent of another. But this is simple. It covers a wide spectrum of errors we have observed in our tracking data, and it is easier to solve because it's a convex problem. Now I will briefly show you some results from this two-step post-processing. One is fragment association, and another one is trajectory smoothing and rectification. Now you can see the comparison before and after post-processing. You can see that the gaps has been filled. It is actually a challenging procedure, especially during the slow traffic, because a 100 feet wide gap could mean more than 20 seconds of data missing, and it is difficult to predict the vehicle's movement during the 20 seconds into the future, especially during the stop-and-go traffic. But during the faster traffic, the matching results are actually pretty good. We also validated the algorithms from a 3-minute worth of videos using the manually labeled bounding boxes to obtain these quantitative results. So the highlighted fields are improved due to the data association alone, and other metrics are standard multi-object tracking metrics, and they're improved as a combination of both the data association and trajectory smoothing. In conclusion, I presented today 2 novel data post-processing algorithms to solve the data quality issues that we observed from the raw tracking data. The first one is the online fragment matching algorithm that can correctly associate the majority of the fragments. The second one is the convex program capable of rectifying trajectories to impute missing data, smooth those noises from the signals, and remove the detection outliers. Of course, there are many ideas for future improvements. For example, we can consider more expressive features for data association, such as appearance embedding, when we have more detection information of those vehicles to determine if 2 fragments should be matched together. We can also consider other features for trajectory smoothing formulation, for example, making sure that no 2 trajectories are overlapped. So these are all the contents I like to cover in this video. Again, the details of the project are listed in the description box below, where you can check out the papers, our website, and most importantly, the data. If you have suggestions for improvement, please also feel free to let us know. Thanks for watching, and I'll see you next time.